is very beautiful, and it's really nice to be with everyone here. I'll talk about estimating Lyapunov exponents with regularity. Of course, that's a very general statement. This work, pretty much everything I'm going to talk about, including some stuff that's in progress, it's all pretty much joint stuff with Jacob Bedrossian and Alex Blumenthal. So let me give you a very big picture view. So I have quite a few things I can talk about. We'll see whether I fit them all in. If I don't, it's okay. But to give you just a general motivation, let's think about basically something Jonathan was talking about. Let me consider an SPDE with some nonlinearity, and let's say this is, I'll write it like this, something which is damp driven. Okay, so we have some positive definite matrix, it's a little bit small, and then we have some noise, which I'm going to scale in a very particular way, like this. Of course, I did what Jonathan does. I didn't put the DTs in there. I'll do it like that. So there are many PDE like this. So let's think of this as an SPDE and sort of damped driven. And essentially, you think of this as like, okay, I have some nonlinear evolution equation. This thing, can maybe be something that's arising from an infinite dimensional Hamiltonian system. So we can think examples are like fluid mechanics, but also some nonlinear wave equations. There are many PDE like this, and I'll give more specific examples in a second. And then what we want to do is we have a small amount of dissipation. So this could be like viscosity for fluid mechanics, and then a little bit of driving. And we scaled them in a way because, as most of you know, with primary motion, this is the right sort of scaling to balance the dissipation. So this kind of scaling is known as fluctuation dissipation. Okay, depending on the exact context here, what is often observed in nonlinear systems like this is that when you start to scale down the dissipation and the noise as well, it starts to exhibit lots of instability. And this is something that I want to understand in a little bit more detail. So specifically, I mean, in many circumstances, if this damping is really strong, you may end up with just sort of a 1-point random attractor. And then as you start to take epsilon down to 0, you get a series of bifurcations. Instability starts popping up more and more and more. You start getting an unstable manifold that starts to develop and get really big. And you end up with a random attractor that starts to grow in dimension. And so, okay, this is ambitious picture, and particularly trying to say anything about that is also pretty tricky to do. But this is the kind of thing that I want to try to understand here. So let me just give you a couple examples that I'm particularly motivated by. But as I mentioned, we consider the 2D stochastic Navier Stokes equations, which are of this form, with the nonlinearity is bilinear, the usual Euler nonlinearity. But we could also consider things like the stochastic Ginzburg-Landau equation, or sort of damp-driven NLS. General other nonlinear wave equations. Both of these things are sort of observed typically to be extremely chaotic, particularly when you take epsilon pretty small. But there are a whole host of other types of PD. In particular, one that's interesting are integrable or completely integrable. And I want to make a point about this because this case doesn't quite fit into the paradigm that I mentioned, where an integrable system without damping or dissipation is not going to be chaotic. But one of the things our methods shows, or it gives a technique for showing that when you put a little bit of noise in there, it induces a strong chaotic response. This may, if it's not something you thought about before, may be a little bit surprising that I take something that is very much not chaotic, I perturb it a little bit, and then it becomes very chaotic. So I'll try to give you some insight into maybe how that could happen. But there are a whole host of other things. So things that fit into this are actually just the 1D NLS setting, or things like KDV and so on. There's really quite a few of them. So when I talk about instability, there are a number of ways to try to understand it. But the way that I'm going to consider is linear instability. And in particular, I'm going to think about, so suppose we linearize. So that is, let me define some flow map phi t, let's say on my solution space. So this is the thing that sends the initial data to your solution at time t. And if I linearize it, typically, let's say we call this thing the Jacobian, like this. This thing solves the linearized equation. So that is, I sort of take the derivative of the nonlinearity. But here, I'm thinking about putting noise, which is additive. That's really the only type of noise I'll be considering here. What you end up with is this equation. And what typically happens is that this equation will blow up exponentially fast if there's some instability. And we can try to capture this by what's known as having a positive Lyapunov exponent. The main form of instability I'm going to consider. So that is, I'm going to define lambda1 to be the limit as t goes to infinity, 1 over t, the log of the magnitude of the Jacobian, and being a little bit loose about the exact norm, but in fact, it typically doesn't really matter the norm you're taking, specifically if the equation is regularizing. So if this is like a Laplacian or something like that. Lyapunov exponents typically are norm independent. So we say that this is a positive Lyapunov exponent if this asymptotic limit exists and is positive. Now, this, for these kinds of PDE, is very hard. In particular, there's no, as far as I know, no known results of a positive Lyapunov exponent for any kinds of systems like this. In particular, for many things like this, especially if they have dissipation, even showing, you can show that the Lyapunov exponents exist by sort of general multiplicative ergodic theory, which I'll talk about in a second. But even showing that lambda1 is not equal to minus infinity. Okay, so there's one open question, but I don't suggest you try to solve that, at least not yet. Although if you do, please.
Minus, right? Yeah.
Did I? Oh, sorry. Yes, minus. Thank you.
Very positive.
Yeah, that would be that'd be a dream. We know it's not infinity.
I was gonna say, I think we know it's not.
Well, maybe for like 3D Euler or something. Instead of considering, yep.
Yeah, so the noise is additive and it's just on low modes, or?
Yeah, I'll be precise here because I'm not actually going to do infinite dimensions. So I know everyone's doing PD here, and what I'm going to do is do finite dimensions. To convince you with some of this talk is that even though I'm doing finite dimensional truncations of PD, this is still extremely hard to do, and they're extremely complicated. So it's already hard enough to do this, and I'll try to give you some ideas of where we heavily use finite dimensionality and where things are challenging to go into the dimensions. If I consider finite dimensions, I'm going to consider a class of models, and I'm going to define a drift. The noise I'm going to write a little bit more explicitly now, which is just some sum of constant vector fields. Okay, so here we're going to think of as these x caves. Although, typically you can just think of things some orthogonal basis of the space here. Right? And this f is going to be something that looks like n of xt plus epsilon a, where this is some positive definite matrix, and this n is now, I'm going to take it to be divergence free. So this is a very typical form you'll get if you take any of these PDE that I mentioned and Galerkin truncate, or truncate them in sort of whatever way you want. So specifically, it's convenient, particularly if you're trying to truncate PDE, and some of the circumstances we're going to do, it's natural to try to do it in Fourier. Okay. So before I do that, let me just state a couple conditions we're going to assume. So I'm going to consider basically, that for the rest of this talk, we're just going to be doing SDEs. Or we're going to consider SDE of this form. Now, there's a lot of PD involved here because, in fact, I mentioned where you're going to use regularity to estimate Lyapunov exponents. So in particular, we're going to estimate certain stationary measures associated with this and their regularity, and certain stationary measures associated with certain augmented processes and their regularity. And we're going to relate that to information about Lyapunov exponents. And we're going to use PDE methods to do that. And so the Galerkin truncations, I'll be precise about certain models in a second. We're going to assume two things. We're going to assume that they're hypoelliptic. Talked about already. And so specifically what I mean by this is that these vector fields here and here, they satisfy Ormonder's condition, or in particular the parabolic Ormonder condition. So what I'm going to assume here is that I'll write it like this. If I take the noise vector fields, xk, which are just constant vector fields, and I also take the first commutator as a drift, and the noise vector fields as a collection, that this Lie algebra, and what I'm going to do here is, anytime I put a subscript on Lie algebra, this means just evaluate all the vector fields at a particular point, if this thing is equal to this fixed. Sorry, I should have mentioned. I'm going to take all these, just for simplicity, all these things in R. Although we can treat these on more general manifolds.
You don't mean prime motions, you mean the X are the.
So yeah, the whole process, yeah. Okay, so we assume it's hypoelliptic. So this means that the Lie algebra generated by all these things, if I take the span of all possible brackets I can take with these vector fields, that if I evaluate to the point that these span the whole space. And so this is one. And two, okay, it's a kind of annoying assumption, but I'm going to assume that the nonlinearity satisfies what's known as the cancellation property. And there may be just a couple people in the room who know why that's necessary, but essentially the point is that this kind of thing will give you regularity, and it comes very close to giving you uniqueness of a stationary measure. But unless you have a little bit more information on the nonlinearity, you don't necessarily have uniqueness. So both of these conditions, these both imply that there exists a unique stationary measure.
Oh, yeah, if you want, you can write on the board behind it.
Yeah, I'll see how it goes, and if it really fails, I'll make the next one. There exists a unique stationary measure for this process, and it has a density rho with respect to Lebesgue. And in particular, rho epsilon is C infinity smooth. At least if I'm applying out of the box Ormonder theorem, a little bit of some uniqueness. This is kind of what Jonathan was saying. You put a little bit of noise on, your goal is to get a unique stationary measure, and in particular, everything is smooth. Right. Once you have this, we're going to use this, but this also implies, as Jonathan mentioned as well, that this is ergodic. And so we actually have sort of a dynamical system which is ergodic on a state space. So now let me give you, actually, let's say the primary example that I have in mind, and that is, let's take 2D Galerkin stochastic Navier Stokes. What I'm going to do is I'm going to fix some n greater than 1, which is the Galerkin cutoff, and I'm going to define the truncated lattice minus 0 to be just a set of all L, in the two-dimensional lattice minus 0, whose norm is less than a particular n. And what we do is we just take the Euler equations and you just project everything onto this lattice. And so in particular, what we do is we're essentially just setting the nonlinearity x to be this bilinear thing, and explicitly in Fourier space, this thing is given by the sum over all. Sorry, let's say the L component is the sum over all L, which can be written as J plus L. Or sorry, the sum over all J plus K that can be written as L of J perp dot K 1 over K squared minus 1 over K squared times xj. Okay, so we think of a solution here, x as being a collection of these vectors, or these Fourier coefficients indexed by the lattice. All right, and this is something, these are complex numbers. So, this is the model I'm going to mainly consider. The reason I'm writing this down is because I will try to tell you something about its form in a little bit. So in particular, the exact structure of this form will play a very important role. Okay, so this is, let's say, the model that we have in mind. And we want to show something about its top of the output epsilon. So let me state for you a theorem. Oh, thank you. I didn't even try. So let's consider this this nonlinear system. So essentially, let xt solve hypoelliptic. Galerkin stochastic Navier Stokes. Hypoellipticity, for instance, proved by, at least for this system, proved by Jonathan and Wayne on show that, in fact, this is also true for the infinite dimensional system. If you take noise, which is only supported on 2 Fourier modes, which are of different length and not on the same Fourier shell, then the whole thing is hypoelliptic. And so therefore you have this smooth measure. So if you solve hypoelliptic Galerkin Navier Stokes, then the top Lyapunov exponent goes to infinity, divided by epsilon, as epsilon goes to 0. And I should remark, there is a small caveat, which I'm not writing optimally. You need to take the cutoff big enough. Okay. So let me truncate Galerkin Navier Stokes and take the cutoff bigger than 300, which is within the realm of computation. Then the top Lyapunov exponent divided by epsilon diverges to infinity. So in particular, this means that there exists an epsilon such that for all epsilon greater than this epsilon star, we have lambda 1 epsilon strictly positive. Okay? So this is showing this effect that as you take epsilon small enough, eventually the Lyapunov exponent becomes positive. All right. So first off, so we can prove this theorem in the 2D case. It's not been proved in 3D. And there are a host of other PD that we'd like to try to apply this to, but there are just Galerkin truncations of PD, but there are some other roadblocks that get in the way. So I'm going to try to outline very roughly how this proof goes and the technique that we apply, because the technique is let's say, more broadly applicable to other PD. But I'll try to make it clear what some of the sticking points are in the theme with for this kind of a system. I'm brushing a lot of stuff under the rug, particularly, even to get existence for these things, you do need to have some kind of Lyapunov structure, which I don't really feel like talking about. But let's just assume that's all okay. What I'm going to consider now is first, for stochastic systems like this, we have a very powerful theorem called the multiplicative ergodic theorem, which not only gives us existence of Lyapunov exponents, it gives us a full Lyapunov spectrum, and it tells us a little bit of information on sort of a subset of spaces on which we expect to see those Lyapunov exponents realized. So specifically here, let phi t omega be the stochastic flow associated with this ST, and then what I'm going to define here is lambda of v is going to be the limit as t goes to infinity 1 over t log of p phi t acting in some direction. Now, already just by the sub-additive ergodic theorem, which is something that Scott had mentioned, we can actually show typically that this thing has a limit and it exists, and it depends on v. And not only that, but by more ergodic theory due to invariance of things, this is the key point about the multiplicative ergodic theorem, is that lambda of v only takes finitely many values, at most n values. And these values are, I'm going to write in terms of their distinct values, but there are m of them because there can be some multiplicity. And moreover, we have that lambda of v is equal to lambda I for all v in some subspace fi minus fi plus 1. So this thing depends on x. Okay, I'm not really going to talk too much about this because it goes a little bit beyond, but there's a whole filtration of subspaces. And as you go down, as you go smaller and smaller in subspaces, the relative complements give you exactly the set of vectors that achieve each succeedingly smaller Lyapunov exponent. right? So now that we have these Lyapunov exponents, in fact, our strategy, it's a regularity method. In fact, the idea is date way back to say Furstenberg and maybe and people before. And it's a commonly used idea in dynamics, which is to say, let's take the derivative of the flow, and we want to think of this as an element in GLN. Okay. And part of the idea is to understand first, let's see how this thing behaves hypoelliptically. Okay, so our goal is to study sort of the augmented process. Okay, and this thing, if you want to be technical with it, is living in some kind of frame bubble, but here everything's flat, so it's not really a big deal. And we want to understand this augmented process in particular. We want to show that it's hypoelliptic. Okay. Now, what do I mean by hypoelliptic? I mean, okay, now I have this thing evolving on some kind of very nonlinear space. If you are a stochastics person who doesn't like working on manifolds, you have no choice. So you have to use geometry here, unfortunately. But it is not too bad. So the main idea is this: if I have this diffusion, in fact, I say that this process is hypoelliptic, especially if I already know that X is hypoelliptic. It has to sort of transmit its noise into the next piece. So this is actually an extremely degenerate diffusion problem, which has it's actually a very challenging hypoelliptic problem. But the idea is that I can define a matrix subgroup, call it MX for every X, and R. Defined in the following way. It is, I take the gradient of vector field X, I subtract its divergence so that this thing is actually an SLN matrix, not traceless. And these vector fields belong to the Lie algebra that I had written parabolic, for this parabolic Ormond condition. Okay, and we're going to require that they vanish at 0. Okay, so this let me say it in normal terms. I look at all possible vector fields I get from my Lie algebra here, and then I look at the matrix algebra at a fixed point generated by their linearizations. Okay, so I'm saying I have this full linear algebra. This gives me all possible linear motions that those vector fields can generate. And this thing ends up forming a subgroup of SL and little SLN. So these are all traceless matrices. Okay, and that's a group, it's a Lie algebra with respect to the matrix commutator. Right. And so when I say hypoelliptic, I mean for all X in Rn, that we have Mx is equal to SLN. Okay. So this is sort of the, let's say, the key matrix hypoellipticity assumption that we're going to make in order to use regularity. Of course, we can actually weaken this a little bit, although you lose a little bit of information, and the only way we know to prove anything is by proving this anyway.
Sam, what's after the one?
Divergence.
So you're taking a gradient and you're subtracting the
Oh, there's an I. Sorry, identity.
Okay.
Yeah, I'm making it traces.
Yeah.
So what we want to do is understand what this implies. So okay, first off, I've augmented this process. I've gotten some hypoelliptic regularity. Unfortunately, this process is not good for a lot of other reasons, and it's mainly that this d phi is unbounded. Okay. It doesn't. So if I want to understand, for instance, the stationary statistics, I really can't because I don't have like a good Lyapunov function on it. I won't be able to get it. So the strategy is actually, in this typical extent, is to look at this thing's group action on a set of let's say homogeneous spaces that are particularly designed to work well with matrix groups. I'll be more precise in a second. So specifically, what we're going to do is just consider the space of Grassmannian. So that is, or let's say GRK or N. This is just the space of k-dimensional subspaces. This is an assumption. So I'm going to assume this is hypoelliptic. I'll prove this for for 2D. Well, I'm not going to prove it. Really. It is proof for 2D Galerkin stochastic method. So if I look at this Grassmannian here as a space, this thing is naturally acted on by matrices, right? So if I take any subspace of Rn, I can take d phi t acting on E, and this I can identify with another element of GRK. Right, particularly because d phi is invertible. Okay, so I'm sort of watching these subspaces move around, and the important point is that if I have SLN hypoellipticity, so essentially MX lift my process to the Grassmannian, where I'm going to put square brackets around here. I mean the hyperplane or the subspace associated with this image. Then this is hypoelliptic. In particular, the Grassmannian is a bounded manifold, right? Essentially, it's like beds like a sphere into a certain space. And so, in particular, that means that this thing should have nice, good, long-time stationary statistics. So, we'll be talking about this in just a second. The reason I'm putting this in here is because, two things. First, what we'd like to understand is stationary measures. Okay, so I'm going to define new epsilon k to be the measure associated with this lifted process. That because it's hypoelliptic has a density with respect to the uniform measure of the Grassmannian. Okay, and these are the things that we're going to try to study regularity for. And in particular, these will be the things it'll tell us information about the output exponents. So the way that we do this is through Fisher information. Specifically, let me give you a generator. So the generator for this finite dimensional process here, I'm going to write as so I'm thinking anytime I write a vector field, I think of this as an order 1 differential operator as well. So this operator right here, associated with it, I'm going to define a Fisher information acting on some function f to be the sum in k, 1/2 the integral of xkf squared divided by say dx. Okay. Now, one of the things that we know about Fisher information, in fact, this is kind of like almost the kinetic theory argument. If I take this thing, I know that L star of my stationary density is equal to 0. Formally, if I take this thing, I multiply by a long row, integrate by parts, and use just a little bit more of something I'm not going to explain in full detail, you get the following identity, which actually says that epsilon times the Fisher information, rho epsilon, is equal to negative lambda sigma, where lambda sigma is the sum of the Lyapunov exponents with multiplicity counted. So some of the exponents have some multiplicity with them. So I sum them all up, and if they have multiplicity, I multiply by the multiplicity.
That's a sign function of epsilon.
That's a sigma. Yeah.
Sure.
And in fact, yeah,
Do you not know that the stationary measure is unique
we do for this one.
for now?
And in fact, you can also show it for all the, it depends on the system actually.
Okay.
Yeah, so for Navier Stokes, you can show it both unique. For other things, it's actually trickier. So for Ginsburg Landau, it's potentially not unique. But that's kind of the, so if this thing is equal to sum of the Lyapunov exponents, which for any of these systems with dissipation is actually equal to epsilon times the trace of the dissipation matrix. Okay, because things are divergence free. This is like sort of a limiting determinant formula. So what it's telling you is that Fisher information of a process is equal to the sum of its Lyapunov exponents. All right. This is one case where heavily using finite dimensions. Okay. The trace of Lyapunov is infinite. So we have a huge divergence there. But let's stick in finite dimensions. So what I'm gonna do now is say that, well, if I know that's true for the Lyapunov exponents.
So you don't think the sum of the Lyapunov exponents is infinite?
Oh, then, no, it's definitely infinite question. Yeah, that's true. It's just not useful. Yeah. Is that if I lift for the Grassmannian, this thing has Lyapunov exponents that, it has the same Lyapunov exponents, lambda 1, lambda 2, lambda m. But it also has, on its Grassmannian part, it has a whole other host of Lyapunov exponents, lambda I minus lambda j, for all I, which are starting from k plus 1 to m, and j. And so what this says is that actually, well, if I lift my process to the Grassmannian and think of that as its own dynamical system with its own Lyapunov exponents, I take its Fisher information and I sum those up. Okay, so what this tells me is that the Fisher information, or epsilon times of epsilon k, in this case is actually equal to n times lambda less than k. So this is the sum of the first k, the Lyapunov exponents, plus k plus 1.
K was the dimension of your Grassmannian.
K is the dimension of the Grassmannian. Okay, so we have this formula for the Fisher information. It relates it to the sum of the first k Lyapunov exponents and this remaining minus. Oh, it's minus there. Now let me mention how to use this. But okay, I can say what needs to be said. So the important point. Oh. The important point, particularly if we want to say information about the first Lyapunov exponent, it's useful to take k equal to 1, because this will tell you something about lambda 1 minus the sum of these Lyapunov exponents. So if I take k equal to 1, then the formula for the Fisher information, and I'm just going to submit the 1 here, is equal to n times lambda 1 epsilon minus lambda sigma. Sorry, just lambda sigma. And what I'm going to do is, so in some sense, I'm thinking of this is like an a priori estimate on the PDE, because I got it by integrating by parts. And in fact, if I divide by epsilon, it gives me n times lambda 1 epsilon over epsilon minus, and remember this is epsilon times the trace of a, so it's or plus the trace. Okay. This is the signs. Did I get the signs wrong? Oh, no, sorry. Yeah. Okay, so we get something that looks like this. Now, I told you that lambda 1 over epsilon goes to infinity as epsilon goes to 0. All right, so let's say the opposite. Let's suppose that lambda 1 over epsilon does not go to infinity and it remains bounded for all epsilon. True, that tells me that as epsilon goes to 0, the Fisher information is uniformly bounded. Fisher information is giving me some form of regularity. Okay, but it's only taking derivatives in the x values, so it's actually very degenerate. So that we have sort of a key that, well, if I also use the fact that f epsilon is the density and it solves a hypoelliptic PDE, then I can show the following. So the theorem basically says that, okay, I'm going to be a little bit sloppy here, but if the vector fields f epsilon, and I'll explain this in a second. Next k. So this just means the vector field, and then there's a natural way to lift it up to the k equals 1 Grassmannian, which is the projective bundle. If this thing is uniformly in epsilon hypoelliptic, which is typically going to be extremely small, but fixed and independent of epsilon, such that we have the following lower bound f epsilon. That is, I can measure it in the Sobolev space, S star U, and this thing is bounded by 1 plus the Fisher information, that epsilon, and maybe it should be squared. Uniformly in epsilon hypoelliptic. So
That's an epsilon.
Oh, that's in epsilon, yeah. So I'm doing a little. I don't want to make it precise because it's kind of technical to write down, but it essentially says that the bracket condition for this I have to be able to span in a way that does not depend on epsilon.
Okay, so it's just the algebraic span. It doesn't say anything about the sign span.
It does a little bit, yeah. I need some quantitative lower bound uniform epsilon as well. But this is like a quantitative Ormond theorem. All right. It says that if I can control the Fisher information, which is very degenerate, I can actually control the tiniest little breadth of regularity in all directions. And this also holds in the Grassmannian as well. So I can also do it on the much bigger space. I have a uniform and epsilon bound. And so if I work in the contradiction hypothesis, yeah. Yeah. I will. I'll point it this way. If I work in the contradiction hypothesis, this thing I'm assuming is bounded uniformly in epsilon. So that means I have a uniform and epsilon bound on the Sobolev ring. What does mean I'm lifting everything up to the tangent bubble? So I should write like this here. Up to the projective bubble. Okay. Now this is one of the key points I want to get across here. Is that once I have hypoellipticity and once I'm able to do this, having a absolutely continuous measure on a dynamical system like this is impossible. Okay, and there's sort of this is kind of a larger program, let's say, is that once you have this uniform epsilon regularity, you can take a zeroized limit, get an absolutely continuous measure, and this can't happen. Okay? And the reason is basically that if you look at things in projective space,
So that's the projective dynamics.
that's the projective dynamics. If you look at things in projective space, think if I give you a hyperbolic saddle and I only look at the length of the vectors moving around here. If I have an unstable thing, everything gets sucked up to the unstable thing and everything gets pushed away. So there's sinks and sources all over the place. But in particular, if I have strong unstable directions, I get concentration of measures. So if I have an absolutely continuous measure here, which is invariant for this dynamics, I just run it through and everything should collapse with the unstable thing. So this assumes that you can find any instability for this equation. All right. So I'm probably trying to do it over time already. So I will give you a formula. I take the derivative of the flow for just the Galerkin-Euler equation. In fact, this is true for any bilinear problem, and it's true in infinite dimensions. If I linearize it in the direction, so think of this, Euler flow is always constrained to live on a sphere. If I linearize it transverse to the sphere, that's pointing also in the direction x, then I can write its solution, exact solution of linearized Euler, which I can write directly in terms of the solutions of Euler themselves. And what you see here is I have this growing factor of p. And in particular, this implies, although it can take a very long time, that if I wait long enough, just due to Poincare recurrence, that if I wait until I reach a point where this set is bounded below by some number, eventually this t gets very big and I will diverge. And that's all you need. You don't need exponential growth. You just need to show that the gradients grow unboundedly, and it'll contradict having a smooth measure like that. And that's really how you unwind it all. So okay, I'll leave it there because I think I'm over now.
Questions? Could you just give a brief conclusion, this cancellation and like how common
Right. So basically, this is satisfied by Euler. And in fact, the things you have, if you have an odd dimensional polynomial nonlinearity, it's fine. If you have, and then you don't have to satisfy this, so I kind of overstated a little bit. It's when you have even dimensional nonlinearities, there's this issue with trying to, with control theory. So one of the things is if you want to get uniqueness of the stationary measure, you should show some regularity, like you have some strong Fowler thing, but then you also need to show that the supports have some overlap for two, let's say, two different stationary measures, or let's say you just want to show that any measure is supported everywhere, or something like that. The problem is when you have this bilinear, if you just have a bilinear nonlinearity without more information, there are just fundamental restrictions on what you can control to in the space using noise. Or maybe Jonathan knows this.
I mean, my question is, but I when you call it cancellation, I wasn't sure that. I mean, I always said that even though it looks bilinear, it's really the right thing. It's a relative degree.
Yeah.
and it's relatively odd.
That's right. You guys wrote a paper on that. Yeah.
It's relatively odd because there's no, you guys know this.
That's right. Yeah.
Right, there's no, I mean, because there's no terms on the diagram.
That's right. Exactly.
In a quadratic form.
That's right. Yeah. That's
Is that
right.
what you mean?
That's what I mean. Yeah. That's right. So it's really being like if
It's time reversal.
Okay, sure.
There's no x.
Well,
xi squared.
I don't know if it's just time reversibility.
Well, in a
Yeah.
very strong sense.
Yeah, that's right. It may not be. Well,
Projective.
no. We need it for the ergodicity of the base too, right? I mean, that's necessary.
No, I thought we could use some return. No,
Okay.
We need it for projective.
Yeah.
Yes.
So you prove controllability on like the on the Grassmannian space.
Yeah.
That's pretty
Well.
hard, right? Or was it?
Well. So I'll admit. Okay.
Like, do you prove like the controllability, like what you do
Yeah.
with this, but for the matrix
So,
space as well?
you do for the matrix space, and then it works for the Grassmannian, and it works for any lifting. It works for project. Like there's a natural way to say that once you have the matrix one, any lift, because it's a Lie algebra isomorphism, it just works. So you can use the Lie saturate, whatever arguments you want to do, and they essentially work the exact same way. I'm not sure I have great intuition for, I mean, especially not specifically for Galerkin Navier Stokes. I don't have any. Okay, so in general, there is sort of a kinetic theory-ish way to see this as well. If you're interested, I can just show you very quickly. Essentially, it's Fisher information. So the law of any process that I want to have solves like a Komondorov equation, right? So let's say it solves. I'm just going to write it in more general form like this. Okay, so I have this equation. If I take the derivative of its entropy, I mess up the exact signs here. This produces two terms. Okay, and the reason for this is that this thing is not conservative. All right, so I have the divergence that comes up from this, and then I have the Fisher information. So what naturally shows up here is that I'm going to screw up the sign. Let me think. The derivative of this thing, and so what it's telling me is that this is sort of an entropy production, and this is an entropy dissipation. Okay, and when I'm sending time to infinity and dividing by t, let's say this should be. That's actually all good. If I integrate the whole thing and divide by t, send t to infinity, then and the dissipation should end up balancing the production, or at least if you don't have strong convergence, that you'll have an inequality, which is also good enough. But so this sort of statement is saying that for these kinds of systems, if you look at the law, the entropy actually has this thing that in the long time limit on the stationary, the production and dissipation balance, and the production I should mention converges exactly to the Lyapunov exponent minus or n minus 1 minus like this. Yeah. Oh, 2. Oh, I probably screwed that up somewhere else. That's okay. The 2. It's not that important. I mean, that's not the best intuition, but it's another way of saying it.
A question. Something I've been thinking about politically. So suppose you have a SPDE, and where you could have a stable, unstable decomposition. If you do Galerkin truncation, and you look at each of them, you look at the decomposition.
It depends. Yeah. So I think if you were to take like infinite dimensional Navier Stokes, and let's say you knew there was a particular instability with a clear unstable and unstable thing, it depends on the situation. But I mean, in general, if you take the Galerkin Navier Stokes and you truncate it, the instabilities stay there. So there will be another, maybe distorted or slightly Fourier truncated stable unstable manifold. But some of them that are maybe very high frequency dependent might just vanish. So I don't. Okay. So as far as the Lyapunov exponents go, they should converge. The Lyapunov exponents. Okay, I don't know the answer to that directly, although I believe that they probably do because of the fact that the stationary measures converge. And a fact that I haven't really told you, but the Lyapunov exponents can be written as linear functionals of the stationary measures. Now there's some moment issue. Alex might know a little bit more about this, but it's lucky you guys have two of the other authors here. So
Yeah, it's like, okay, you can realize the Lyapunov exponents as averages of linear functionals over some process. It's not the velocity.
No, it's the
process.
lifted
You need to
one.
augment by
Yeah.
this thing, the projective thing, but yeah, so presumably those converge, and yeah, I do suspect the Lyapunov exponents converge. We haven't proven that, don't
quote us.
don't quote us, don't bet your life on it, but it's probably.
I see, I'm putting $5.
$5? All right. $5 is not true.
To be sure.
But I know systems that use fine-dimensional Galerkin approximation have one invariant measure. Are you sure that the invariant measures converge with Galerkin approximations?
Yes. The possibility, though, is that the exponents go to minus infinity, and there's.
Because I know examples
things could
where,
happen.
I know examples where that's not true. Could you prove it? No, not even proof. No, it's continuous, can't get down to Euler. It's continuous if you bound away from the viscosity away from zero, and then you approach to the.
Yeah, but I mean, for fixed viscosity positive.
It doesn't move, but you're taking epsilon to zero, so you're going to Euler.
No. Okay, there's two different things. I mean,
Right, so I just want to make sure,
Yeah,
I think
yeah.
that's maybe
for fixed epsilon,
be precise.
yeah,
Yes.
if you want to take epsilon with n,
No,
that's
no,
impossible.
if you fix epsilon and take n infinity there, you
Yes.
know it's continuous.
Okay,
That's
yeah.
right.
That's
That's the paper.
yeah.
Let's go have some coffee. Thank you.